All right, we're talking about solids, and three-dimensional shapes are called solids. A solid can be things like a sphere, a cylinder, a cone, a polyhedron, and we all have experiences with these kind of objects. We know, cans look like cylinders. We have ice cream cones. A polyhedron is kind of a unique word, but it's things again that we've seen before. A polyhedron, if the surfaces are polygons, where the closed three-dimensional figure is formed by 4 or more polygons that intersect only at their edges, this is a polyhedron. So a box, a pyramid. We're going to see a lot of polyhedron in this episode, in this video, but there's a lot more that you're not even going to see here in this video. There's endless, infinite amounts of different shapes that we can form with polygons and make three-dimensional like this. We want to classify these solids. This right here would be a cylinder. This right here is simply a polyhedron. And this is a cone. We'll get into more specific names of polyhedron in a second, but right now, based on what we've talked about, this is formed by 4 or more. It's actually formed by 5 polygons there, connected just at the edges. So it's a polyhedron. Finally, well, not finally, but we got some more stuff for us. The face of a polygon is going to be each one of the flat surfaces. The segment that is the intersection of two faces we call an edge, and the vertex, of course, is where the edges meet. So right here in this polyhedron, we'd have 1, 2, 3, 4, 5, 6, 7, 8 vertices. A prism is a specific polyhedron formed by 2 parallel congruent polygonal bases connected by lateral faces. These are all prisms. Notice how we have here we have 2 triangles that are congruent. Here we have 2 hexagons that are congruent. And here we have 2 quadrilaterals that are congruent. And all the faces that are connecting these 2 bases are all rectangles. It doesn't have to be a rectangle. It could be any kind of parallelogram. Could be connected by parallelograms. These could be shifted over. As long as these are parallel segments, then it's considered a prism. All right. Jump the gun on that one. I'm sorry about that. It doesn't have to be a rectangle as long as it's a parallelogram where you're good. The base of a prism is one of 2 congruent parallel faces. All right, so the bases are, like I was saying, those 2 hexagons, those 2 triangles, those 2 quadrilaterals down there. And a face of the prism that is not a base is called a lateral face. So they're all faces, the base is included, but a lateral face are those parallelograms connecting the 2 bases. Now a pyramid, we know what pyramids look like. We don't just have to have a pyramid with a square as the base, as is very common to us as we think about the pyramids in Egypt and things. But a pyramid could have a triangular base, it could have a hexagonal base, it could have a octagonal base. Lots of different shapes could be the base, but a pyramid has a base that is any polygon really, and then we have these triangular faces that meet at a common point. So let's classify these. Right here we can see that there is a base with triangular faces. This is a pyramid, and we call it a specific type of pyramid. It is a pyramid. But the type of pyramid is determined by what the base is. The base of this pyramid is a triangle, so this is a triangular pyramid. this right here is formed by two congruent bases, and the lateral faces are parallelograms, so this must be a prism, but it is a specific type of prism. The type of prism is given by what type of polygon are the bases, and this, once again, is a triangle. So this is a triangular prism. Now, polyhedron can be considered regular. A polyhedron is regular if all of its faces are congruent regular polygons. A pyramid is regular if its base is a regular polygon and its lateral faces are congruent isosceles triangles. A prism is regular if its base is regular and its faces are rectangles. And a cube is both a regular polyhedron and a regular rectangular prism. A triangular prism is with equal angular, or a triangular prism with equilateral bases is a regular prism, but is not a regular polyhedron since its faces are not congruent to its bases. A lot of information right there. It will make more sense the more and more examples we see, but this is a big piece of information you can always go back to and reference if we're trying to distinguish if something is regular or not. The diagonal of a polyhedron is a segment whose endpoints are the vertices of two different faces of a polyhedron. Like in this, if we were to try to draw a diagonal could go from F to A. It would be cutting through the polyhedron, and that would be a diagonal. So, classified as polyhedron in the diagram, assuming all the angles of the pentagon are congruent. Okay, that's great. We're told that all these angles are congruent. And so this right here, being given these tick marks that we see, this is a regular pentagonal prism. It's a prism because we have two congruent bases, and those bases are not just congruent, they're regular. So we can see that we have two regular congruent bases that are pentagons formed by these rectangles or connecting them with their lateral faces. So this is a regular pentagonal prism right here. It's not going to be a regular polyhedron because the bases are not the same as the faces. How many edges, vertices, and faces does it have? Well, let's go with edges first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 edges. Vertices, 1, 2, 3, 4, 5, 6, 5, 10 vertices. And faces, 1, 2, 3, should be 5, 6, 7 faces. Yeah. It says name one diagonal segment of the polyhedron. We drew one earlier. FA is a diagonal segment of the polyhedron. Now notice this right here, how many edges, vertices, and faces there are. This is pretty important for us. We have Euler's formula. It says for any polyhedron with V vertices, E edges, and F faces, we have this formula right here. V minus E plus F equals 2. Let's check it with what we counted in that polyhedron. If you're thinking, well, I'm not sure if I counted all these correctly, well, we can check it with Euler's formula. The amount of vertices minus the number of edges plus the number of faces should give us 2. If it doesn't, then we did something wrong. 10 minus 15 is a negative 5, plus 7 is 2. And since 2 equals 2, that checks out. I think we counted these right. If it didn't work out, then it would not be a valid polyhedron. This example says, how many faces does a polyhedron with 12 vertices and 18 edges actually have? Well, we know there's 12 vertices minus 18 edges plus some amount of faces always gives us 2. 12 minus 18 is a negative 6 plus f gives us 2, and so f must be 8. There must be 8 faces to this polyhedron. That is the only number of faces that could possibly create a polyhedron with 12 vertices and 18 edges. Only some application if we're thinking about diamond cutting here. Diamonds are cut to change them to form a rough stone to a gemstone. Here we're starting right here with this, looks to be a particular, it looks like maybe a triangular pyramid there is what we got going on. And we are cutting, notice how they cut right there to cut off the corner of that diamond. They cut it off and it forms a new face, a couple of different edges and vertices there. And then we cut that off, and that was step 2. And we want to know how many are going to be in step 4. So hopefully we can see a pattern here. Alright, so to start, and then we're going to have step 1, 2, 3, and hopefully we can predict how many will be in step 4. So to begin with, how many faces did we have? 1, 2, 3. Looks like we had 3 faces at the beginning. Sorry, 4 faces, because we have to assume there's a face on the back. This is a triangular pyramid, so there's 4 faces. How many vertices? 1, 2, 3, 4 vertices. And how many edges? 1, 2, 3, 4, 5, 6 edges. V minus E plus F equals 2. Check it with Euler's formula. It works out. That's V minus E plus F equals 2. Checked it. It worked. We counted them good. Next step, how many faces do we have? 1, 2, 3, 4, 5 faces now. Added a face. Our amount of vertices are now 1, 2, 3, 4, 5, 6. Added 2 more vertices, and how many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. V minus E plus F still equals 2. We're still checking out. Still doing a good thing on the counting. Notice what happened here. We increased by 1, increased by 2, increased by 3. Let's see if that continues. Our faces for this next step. 1, 2, 3, the one on the back, 4, 5, 6. The amount of vertices, 1, 2, 3, 4, 5, 6, 7, 8. It increased by 2 again. And our edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you really think about what's going on there, you can count all 12 of those vertices. Hopefully it still checks out. V minus E plus F still does equal 2. Good. And notice this pattern. We're increasing the faces by 1, we're increasing the vertices by 2, and the edges by 3. I believe that's going to continue. This would be 7, and then 8 faces would be in step 4. This would be 10, 12 vertices in step 4, and 18 edges we would expect in step 4. Make sure it still works. V minus E plus F does equal 2. So this does check out.